Our final speaker of this session is Mark Rosegrant. Mark is Research Fellow Emeritus at the International Food Policy Research Institute. He's widely published on topics of agricultural policy and climate change events, and he will be closing this session with a focus on the implications on food systems.
Okay, 2 minutes. Okay. Gotcha. Okay. Okay, thanks very much. It's great to be here. What I'm going to do is briefly talk about a couple definitions and objectives of what I'm going to do. Talk about the challenges facing food systems, environment, and food security in the future. Then I'm going to explore some scenarios for more sustainable and resilient food systems. A very brief discussion of the methodology, the modeling methodology. I'm going to talk about some investment scenarios to make agriculture more productive and efficient, and also then some dietary change scenarios, and then just a very brief conclusion. Okay, let's see. All right. So, definition, the United Nations says that a sustainable food system is a food system that delivers food and nutrition security for all in such a way that economic, social, and environmental bases to generate long-term food security and nutrition for future generations are not compromised. So a little bit of a twist, but similar to what we heard from Jess and Adam. Resilient system then has the additional challenge that being able to respond and adapt to shocks and other kinds of uncertainties. So what I'm going to try to explore is what policies, investments, and behavioral changes could contribute to improving income, food security, and nutrition while reducing greenhouse gas emissions and use of water, land, and the rate of conversion of forests. So some of the challenges, I think this audience knows, boy, those colors are different. You're right. So is the slow decline. We see slow decline in malnourishment in terms of undernourished people. The left-hand graph, where we're down from about a billion in the 1990s to around 800 million currently. The number of stunted children has gone down dramatically, but all of that gain has really been in Asia. As you can see in the bottom line, in that middle graph, Africa actually has more stunted children now than it did in 1990. And of course, we have the very rapid increase in overweight and obese children in Africa, Asia, and developing countries overall. So a big challenge ahead there. Micronutrient deficiencies are also pervasive. You can see in the map, you have, for example, extreme deficiencies in India and Asia, but even medium to high levels in most of the rest of Asia. And there's a very large prevalence of specific types of micronutrient deficiencies, such as anemia, vitamin A deficiency, and iodine, as you can see here. Population growth, of course, is also going to be a big factor in determining what happens in the future. Projected increases are shown here for the Africa, south of the Sahara, South Asia, and East Asia. I think because these are the sort of key areas that will determine population growth. You can see the huge growth in population in both South Asia and Africa. So those areas that are most challenged nutritionally and for food security are also the ones that are going to have account for almost all of the population growth in the future. Of course, as we've heard before, it's becoming a much more urbanizing world as well. Evolution of food demand is going to offer challenges. The combination of rapid income growth and urbanization, of course, as we've already heard, is changing diets to convenience foods and fast foods. There's some good things. There is increasing consumption of fruits and vegetables in much of the world at a higher pace with income growth. But of course, also those with higher sugar, fats, and oils. There is continuing to be rapid growth in meat consumption, and particularly in areas where you don't want to have that meat consumption growing. That in turn leads to much faster demand for grains for feed. Half of growth in grain demand is from now through 2050 is likely to be directly for feeding of livestock, including almost all of the maize. That in turn puts intense pressure, of course, on land and water. in terms of water stress risk, this is some work done that IFPRI did with the Veolia Water Company to measure areas under water stress risk. And we found in 2010, about a little over a third of the population, more than 40% of grain production, and a fifth of global GDP is in areas which have significant water stress. And those numbers, as you can see, by 2050 are going to be far higher, with half the population in grain production and nearly half of GDP in regions where water stress is an issue. Climate change is going to reduce crop yields relative to current water. And as you can see here, this is current weather. And this looks at the impact of climate change on biophysical yields of maize relative to 2050 without climate change. As you can see, the heavy losses almost throughout the world there, including in the U.S. And in many poor countries. The U.S. loss, of course, is important because, as we heard, exports are a very important part of U.S. products. The other countries, an important part of food security. So let's now look, turning out, given those challenges, what do scenarios look like? So I just want to briefly introduce IFPRI's impact modeling system, which explores different alternative climate investment futures. So I won't get into much detail, but some of the key parts are in the middle there, where it says impact global multi-market model. That it has a very high level of disaggregation, 159 countries, 154 water basins, and 60 commodities are handled. It does take account of climate change by inputting the results of the general climate models. That work through a crop modeling approach to look at the impacts on yields. It also handles water demand by sector in terms of its influence on water available for agriculture and other areas. And it captures macroeconomic and sectoral trends, including GDP and income growth. You can specify alternative assumptions. And in this particular version is linked to what's called a general equilibrium model, which captures the effects of any changes on the entire economy. So you can look at labor, employment, and GDP throughout the economy, the impacts of what happens in the agriculture sector. And then we generate estimates there, as you can see below, of yields, commodity prices, trade, employment, household income annually. And with post-solution models, we look at hunger and nutrition. The two indicators I'll look at today are the number of hungry people, which is based, the estimates are based on the FAO methodology of looking at the number of people below a specific hunger line in each specific calorie consumption in any given country, and and stunted children, which is based on the econometric results that Lisa Smith and Lawrence Haddad have estimated. So what kind of scenarios are we going to look at? So first, I'll start with these basically agriculture investment and productivity scenarios, and we have different types of scenarios with and without climate change, and here we're going to use the RCP 8.5, which is the more severe climate change scenario from IPCC, with the shared socioeconomic pathway 2, SSP 2, which is sort of a moderate or a medium level of GDP growth. And then we're going to show the same scenario, but with additional investments in the agriculture sector to improve productivity and efficiency. I'm going to concentrate mostly on what I'm going to call the comprehensive, what we call our comprehensive investment portfolio, which is an increase in investment over current projections of investment in agriculture sector by country of about $25.5 billion per year, which is above about a $38 billion current annual expenditure on agriculture, which is, of course, not that big amount of money compared to other expenditures we see. So we're going to look at how that affects the relevant outcomes relative to a baseline projection with that lower level investment level. The kinds of things we're going to look at are ag research and development, including investments made by the CGR, the global irrigation global system for the main international system, and national agriculture and research system investments in ag R&D to increase ag productivity. We're looking at different water scenarios, including expansion of irrigation systems, together with enhancing water use efficiency. And we also look at a soil management scenario that looks at system level efficiency, but also looking at no-till integrated soil fertility management and rainwater harvesting. Finally, we look at investment in the rural infrastructure sectors. So let's look. This covers a whole lot of effects here. So this is a summary effect of different scenarios. So we have, along the left-hand side, different types of ag R&D investment scenarios. And the next group is high irrigation investment with water use efficiency, and then the one with integrated soil and water management and soil fertility management. We then have a RMM is rural infrastructure investment, and then the comprehensive scenario that I mentioned is along the bottom. So we look at different types of outcomes, and these are all computed relative to the 2050 baseline. And so we have GDP per capita, ag supply, hunger, stunted children, and 3 environmental variables: water use, greenhouse gas emissions, and forest cover. So we can see here, let's focus on the comprehensive scenario, given the time available, that we can generate very substantial per capita income increases, nearly 6% by 2050, from these investments in making agriculture more efficient. As would be expected, it increases agriculture supply substantially. It also reduces hunger by 24% and the number of stunted children by 9%. So that's resulting in 120 fewer hungry people and 10 million fewer stunted children in 2050. We get, particularly because of the water use efficiency scenario, you can see that it also can generate substantial reductions in water use, about 11% in consumptive use of water in agriculture. And because of the productivity enhancing nature of in both crops and livestock, you get lower land use, lower number of animals, and more efficient production of animals with respect to methane gases. Ends up generating about a 25% reduction in greenhouse gas emissions by 2050. And that's ends up being about 3 gigatons. So somewhat same kind of order of magnitude that Dave was talking about in terms of making agriculture more efficient. Forest cover, it looks like a tiny number, 0.22. That is a savings about 88 million hectares, but again, not a huge number. A lot of the reduction in area generated by agriculture goes into other types of activities. So, okay, let's look at a different kind of scenario. What happens under reduced meat demand, and how does that affect global security? So we ran a couple of scenarios. In one, it is a high-income scenario where we just forced a 50% reduction in per capita meat demand in high-income countries relative to the 2050 baseline. Then we did it in both high-income countries and a 50% reduction in Brazil and China, which are huge meat-eating countries as well. So let's run through some slides really quickly. First, of course, we get the percentage change in per capita meat consumption in 2050, again, relative to the alternative without the meat reduction. As obviously expected in China, Brazil, and high income, you get the forced reduction. I think an important thing is then that because of that drives down meat prices and results in significant increases in meat consumption in sub-Saharan Africa from the very low levels that they have now, about a 30% increase, as you can see in the middle there, as well as in developing countries. The other thing to note is that the impacts of China and Brazil are even higher than the impacts of high-income countries as well, because of both the large populations and the very high levels of consumption there. You get reduced feed grain demand. Then you also get modest. Well, I think it's a reasonably substantial production change in the percentage in the population at the risk of hunger in 2050. And this results from overall lower prices that induce lower income people to consume more and increase their consumption. So you have lower prices not only of meat, but of several of the grains, particularly maize, but also small changes in wheat and rice. So you get a 9% reduction, for example, in sub-Saharan Africa in the population at risk of hunger, and 6% overall for this scenario. Oops. That turns out in terms of numbers, again, you would bring 60 million people out of hunger in developing countries as a whole, 40 million of those in sub-Saharan Africa. So you do get important distributional impacts from that drop in meat consumption. It also does result in significant conservation of area, where this is millions of hectares of pasture and cropland, and it's above the line because these are reductions, so these are the conserved area. As you can see, again, under the high impact plus Brazil plus China scenario, for the world as a whole, you get 180 million hectares of land saved, and in the developing countries account for about a little less than half of that. So you get a very substantial amount. I wanted to show one other slide then that looks more comprehensively at the greenhouse gas emissions under different meat demand scenarios. This is a slide that Hermann Lotze-Kampen at Potsdam shared with me. So this uses three different scenarios: a constant share of meat in the diets, a very high meat or more meat consumption, and then a less meat consumption. The constant diet is probably the closest to ours. It gives about a 40% increase actually in per capita demand because it goes along with others, whereas ours is about 60% increase. The more meat is about a doubling of demand, and less meat is about a 60% drop. So somewhat similar to what we showed in our scenario. So you can see what happens. Again, this has very large impacts on greenhouse gas emissions, as you'd expect. If you compare the less meat scenario B to A and the one on the top of constant diets, you end up with a dietary change, a reduction of about anywhere from 3 to 5 gigatons per hectare, depending on which baseline. So again, in our agriculture productivity and efficiency scenarios, we've got 3 gigatons reduction in greenhouse gas emissions. This would generate even higher, another 4 to 5 gigatons, which is, if taken together, those are fairly similar to the current levels of greenhouse gas emissions from agriculture. So just some very brief conclusions. So increased investment in agriculture research and development, rural infrastructure, and irrigation and water efficiency does generate substantial increases in supply and income. I think that's one thing we really have to recognize is that in order to generate the income to reach food security and nutritional statuses, you need to produce more food produced by the people in developing countries who still account for as much as 40 to 50% of labor and employment and 20 to 30% of GDP in many of the poorest countries. So you're not going to get that kind of income improvement by importing food. So that's the flip side, that if you can get more efficient agriculture, generate more income and more employment in the countries, that's a big boost for food security and nutrition. And you do it with the higher income, lower prices generated by improved food security and nutrition. You do get improved food security and nutrition. Just a point on prices, that in the US, low food prices hurt big farmers who market all their food, but in most of the developing countries, farmers get less than half of their food, and sometimes 10 or 20% even from very, even middle-income countries from their production. So they also end up being hurt by higher food prices because they're buying a greater proportion of their food from the market than what they're selling. So it doesn't work that high food prices help farmers necessarily in developing countries. As we saw, we also showed then reductions of hunger, stunted children, water use and greenhouse gas emissions and increased in forest area are possible with those kind of more efficient scenarios. But then the dietary change policies, as you saw, is also very powerful, and arguably more powerful in some aspects in terms of greater reductions in greenhouse gas emissions and further reductions in hunger and agricultural land use. So I think we need to really take a balanced approach here and recognize that we need efficient and sustainable productivity growth together with improved value chains and the kind of significant dietary change that we've been discussing here in order to make serious inroads in terms of making agriculture more sustainable and resilient. Thank you.